Okay, this is the part 3 video where I'll talk about what are the control mechanisms that are there to make sure that this 7 millimeters of mercury is enough. So we've got 7 millimeters of mercury pressure creating filtrates. We need to make sure that that's enough. So there's 4 basic control mechanisms. The first one that I'm going to put up here is something called myogenic control of afferent. Now we talked before when we talked about blood vessels that there's 2 ways to control the diameter of a blood vessel. Something called metabolic control, and that one's fairly intuitive, that if there's low oxygen, then the tissue is basically demanding blood, and so the blood vessel will dilate and bring in more blood and more oxygen. Or if there's plenty of oxygen, if there's plenty of oxygen, then the vessel would constrict, save the blood for other areas. The myogenic control is a little less intuitive, and the reason is because we tend to want to think about blood pressure in terms of blood vessels in terms of keeping blood pressure the same. So we would generally imagine that if blood pressure decreases, you might expect the vessel to constrict in order to get the blood pressure back up. But in certain areas of the body, you're not as concerned about blood pressure as you are about blood flow. And myogenic control is all about blood flow. In the case of myogenic control, if a blood vessel if blood pressure were to decrease, then we'd want to actually open up that blood vessel to maintain a flow. You will need more room to make sure that the blood keeps flowing. So myogenic control in terms of the afferent, what we'll draw is, so if we have a standard vessel right here, if we were to have a decrease in pressure, then this blood vessel is going to widen out, it's going to dilate, in order to make sure that they're still getting enough blood flow. If, on the other hand, blood pressure were to increase, then the vessel will constrict in order to keep the flow down. Another way to put that maybe is to put it on a graph of pressure versus flow. If pressure is heading up in this direction, let's do it like this. Then when pressure is high, then the blood vessel will actually be constricted. And when the blood pressure is low, the blood vessel will be dilated. And the reason that would be is because it will keep flow constant. So the blood vessel will try and keep flow constant in response to the blood pressure. A second mechanism that we're going to cover is something called JG cells, or juxtaglomerular cells. JG cells are mechanoreceptors. They sense stretch, which is essentially blood pressure. And where JG cells hang out, they hang out near the afferents. Now there's a few down here too, along the efferent, but mainly they're around the afferent. What they're going to do is they're going to sense if BP is low, they will sense low stretch. What they will do is release renin. Now renin is a very potent hormone, and it has several functions. And it has a rather complex cascade. But at this point, we just need to talk about, we're just going to consider that renin causes the absorption of sodium. So it's going to increase sodium. This will increase fluid to increase blood pressure. And if the whole problem was blood pressure is too low, if blood pressure is too low, then everything will go through so slow that we'll pick back up waste. If we can increase fluid in the system and get blood pressure back up, then we'll increase GFR. If BP is too high, JG cells sense increased stretch, will decrease renin release and decrease sodium absorption. This would decrease fluid to decrease blood pressure. Another mechanism, and this is where I said before, it's very important to draw your distal convoluted tubule coming back up near the afferents, because these cells right here are called macula densa cells. And macula densa cells are osmoreceptors. What they sense is essentially sodium concentration. What they're expecting to see, and when we drew this originally, these little pink dots were sodium, we expect a certain amount of sodium to show up at the macula densa cells. The amount of sodium we expect to show up is the amount that was consumed in the diet. The kidney's role is to get rid of the amount of sodium, balance sodium, so get rid of the amount of sodium that's coming in, match out within. And so the macula densa cells are expecting a certain amount of sodium here. However, if sodium is greater than diets, that means GFR is too high. That means everything flowed through so fast that too much sodium ended up over here. So what the macula densa cells are going to do is constrict the afferents. So if GFR is too high, everything's flowing through too fast, one of the ways we can lower that is constrict the afferent so less blood is delivered to the glomerulus and less filtrate is made. These are also going to inhibit JG cells, which will inhibit renin. Should put a down arrow, decrease renin. If sodium is less than diet, this must mean there's too low of a GFR. And too low of a GFR means that the sodium was able to reabsorb and no sodium ended up back over here in the distal convoluted tubule. So what we need to do is get GFR back up. We can do that by dilating the afferents and stimulating renin. In JG cells. So you dilate the afferents, you get lots more fluid coming in, you make higher amounts of filtrate, and you speed everything up. Now there's one last important control here, and that is the sympathetic nervous system. Occasionally the sympathetic is your fight or flight, and occasionally the sympathetic raises your blood pressure on more of a constant basis, days and weeks. You might think in terms of family problems or some kind of test or finals week is coming up and your blood pressure will be elevated. And the way the sympathetic does this is it alone can constrict the afferents. And if you constrict the afferent, you deliver less blood to the glomerulus. Make this smaller. You deliver less blood to the glomerulus. You make less urine, which means you retain that fluid, and your blood pressure is going to go up. The sympathetic nervous system can also stimulate renin. So those are the four main mechanisms that help to control GFR. And the reason you need to control GFR is because if it's too high, you'll lose things to the urine. If it's too low, waste products will leak back. And you have a very narrow window of control because these pressures are so close to each other.